Welcome back to Applications of Maxima and Minima Part 2, just the examples. Let's do some more examples. Hercules Films is deciding on the price of its video release of its film Bride of the Son of Frankenstein. Marketing estimates that at a price of P dollars, it can sell Q equals 200,000 minus 10,000 P copies, but each copy costs $4 to make. What price will give the greatest profit? So as I read through this, I underlined some things, but let's go back and see what they are. First of all, we want to give the greatest profit. We know profit is always revenue minus cost. Awesome. Okay, let's see if we can find a revenue, see if we can find a cost in this information. First sentence doesn't really matter. It just sets us up, right? Marketing estimates that at a price of P dollars, it can sell Q copies. So Q is the number of copies. Each copy costs $4 to make, so our cost will be $4 multiplied by the quantity of copies. So that's 4 times 200,000 minus 10,000 P, which is 800,000 minus 40,000 P. Okay, but we also need revenue. Revenue is always price times quantity, and price is P, quantity Q given by our equation. We can multiply to get a revenue of 200,000 P minus 10,000 P squared, and these will be our constraints. We'll use these two constraints to make the profit, right? The profit function is revenue in gray minus the cost. Remember to subtract all of the costs. That's why I put it in parentheses. Make sure that negative gets distributed. That's all I did in this next step. And then combine like terms. I have a negative 800,000. I have 240,000 P and a minus 10,000 P squared. And it's really weird that I didn't write it in ascending order, or descending order, descending order or ascending. I didn't write it in any order whatsoever. But that's okay, right? Because we want the greatest profit. The greatest profit, we're going to take the derivative of profit with respect to price. This actually looks like a dp, where the capital P is profit and the lowercase p is price. And when you get a conflict like that, it's all right to write it out like this. It's never a bad idea. Taking the derivative of 240,000 P, where P, the price, is the variable, I'll have 240,000. The derivative of negative 10,000 P squared is negative 20,000 P, and the derivative of 800,000 is 0. Any constant. 8, 80, 800, 800,000, doesn't matter, derivative 0. So we know that the derivative is equal to 0 when 0 is equal to 240,000 minus 20,000 P. We'll add 20,000 P to both sides. Divide by 20,000, we get a price of $12. Problem starts with words. Let's finish it up with words. At a price of $12 per video, the company will maximize its profit. Excellent. Let's talk about American Airlines. Does that even exist anymore? I don't know. It might not. Anyway, American Airlines used to be a real airlines, requires the total outside dimensions, length plus width plus height, of a checked bag not to exceed 62 inches. Suppose you want to check a bag whose height is equal to its width. What is the largest volume bag of this shape that you could check on an American Airlines flight? So I drew a piece of luggage. I got some wheels on it. I got a handle here. There's probably a handle on that side. I'm sure it extends out for a little rolly, whatever. None of that matters. I could get an image of regular boxed luggage, right? A height, width, length. Okay, I know what a box looks like. But if we go back here, length plus width plus height not exceed 62 inches. So L plus W plus H has to be less than or equal to 62. And this particular bag, its height is equal to its width. Right? So the height and the width are the same. It has a nice square base. What am I trying to solve for? All right, so the constraints, right? It told me some information along the way. The question tells us what we're actually looking for, this question or statement of action. What is the largest volume bag? My objective, the volume of a rectangular bag. And we're just going to assume it's a rectangular. I know bags don't have to be, but that's the common. Volume equals length times width times height, and I want largest, so I'm looking for a maximum. So here's what I'm going to do. I'm going to substitute H equals W. So the L plus W plus H equals 62 becomes L plus W equals 62, right? W equals H, so replace the H with a W. L plus 2W equals 62, and I can solve for L as 62 minus 2W. I used one equation to get the other constraint down to two variables, and with two variables I can solve for one of them, and now I can substitute everything into my objective function. Volume is length times width times height. We know L is 62 minus 2W. We know the width is just the width, and we know the height is also the width. It's also equal to the width. So where each of these has come from, we can multiply. That's a W squared over here on the end. And then when we multiply, we'll get 62W squared minus 2W to the third. Now that we have the volume in terms of a single variable and not three of them, we can find the derivative, 124W minus 6W squared. Set it equal to 0. So I'm gonna, why didn't I have 4, 5, 6, 7? That's why. I'm gonna factor out a 2. Yep, just a 2. 2W, I guess. It seems like 6 will go into it, or maybe 3, but neither one of them does. 2 is all they have in common. 124 divided by 2 is 62. 6 divided by 2 is 3. I still have the appropriate amount of W's. So if two things are multiplied together to give me 0, either 2W is 0, in which case W is 0, or 62 minus 3W is 0, in which case 62 equals 3W, and W equals 62 over 3. Now down here I say that W equals 0 is not a maximum. If the width of your suitcase is 0, that's not going to hold very much. It's certainly not going to lend much for capacity. You could do a first derivative test. You could also do a second derivative test. Check this out. My second derivative. Wait a minute. We haven't got to a second derivative test yet, have we? I was just kidding. Oh, yeah, we have. That was in chapter 11. Second derivative is 124 minus 12W. And if I put 62 thirds in here, if we haven't had it yet, then you get a preview of what's coming up. 129 over 1. 12.3, this is minus 4 times 62, and what I really care about is that 4 times 60 is a 240, so that's 248. This is negative. That's all I care about. If it's negative, we know the graph there must be concave down, and so we know that this must be a maximum. And so the second derivative test is kind of handy here. We don't have to do signs and check things in left and right. So now what's our answer? Don't forget, we want the largest volume. What is the largest volume of bag? Well, if W equals 62 over 3, then H is also 62 over 3. And L, we could find, it seems to be that they're all three the same dimensions, 20 and 2/3. The max volume will be cube-shaped. And I didn't finish this answer. 62 thirds all cubed. If I were to throw that into a computer or a calculator, because I'm so planned ahead of time. Yeah, that's me stalling. So we'll have 62 thirds. I'm doing this off screen because why would I want to show you something in a video? I'm doing 62 to the power, 62 thirds to the power of 3, and my calculator's not playing along. 88, 26, 96. So I'm going to say about 88, 27 cubic inches is the maximum value, right? Once I have that L, W, and H, I need to go back in and actually, what is the largest volume? The largest volume is 8,826 cubic inches. All right. Another one, because this is already getting long again. The demand in rides per day for monorail service in Las Vegas in 2005 can be approximated by this equation. Q equals negative 4,500 P plus 41,500 when the fare was P dollars. What price should have been charged to maximize total revenue? Maximize revenue. Revenue is always price times quantity. That's P times our Q, which is negative 4,500 P squared plus 41,500 P. To maximize revenue, we take the derivative, which is negative 9,000p plus 41,500. Set it equal to 0. I'll add 9,000p to both sides, divide both sides by 9,000, and I get p equals 4.61, and the 1 repeats. So they should have charged, to get maximum revenue, they should have charged $4.61 for the monorail in 2005. All right, this one's fun too. I had to throw in a little one of the monorail so we could take a breath before. Number 5. A company manufactures cylindrical metal drums with open tops with a volume of 1 cubic meter. What should be the dimensions of the drum in order to use the least amount of metal in their production? Okay, so a cylindrical metal drum, I'm thinking like a big 50-gallon oil drum, but it's like a soda can. That's all it is. It's just like a soda can, a cylindrical metal drum, only this one's bigger, right? So if I pull this apart, think about it. If you take a rectangular sheet of paper and you bend it around, it makes the sides of the circle, right? And we know that the total distance around this piece of paper will be the circumference of the circle, so that's 2 pi r, and we have a height of h. And we have the bottom, which has a radius of r. So what we know is the constraint says the volume of 1 cubic meter. So a volume of the cylinder is 1, and the volume of a cylinder, we can look up the formula, is pi r squared h. Okay, look that up if you need to. We have the most fascinating gadgets in our pockets most of the time. It has all the information in the world. Look up the volume of a cylinder if you don't know it. But in general, it's the area of a circle multiplied by the height, because you're just kind of pulling it up. All right, pi r squared times h. Now, the least amount of metal. The amount of metal is the actual surface area. So my objective function is to minimize surface area. And surface area will be the surface area of the rectangular part, 2 pi r times h, right, length times width, plus the area of a circle, pi r squared. Well, we know that h can be solved. We can solve for h here. H is equal to 1 over pi r squared, right? Because we know the volume is 1. If 1 equals pi r squared h, then h equals 1 over pi r squared, and I can substitute. This is where we do a lot of work without writing very many numbers at all. So I substitute my h in. Now I simplified them completely. I have 2 pi r over pi r squared. Pi's cancel. This r cancels. I have an r remaining in the denominator and a 2 in the numerator. Plus pi r squared. And then I just rewrote it in terms of, I want to find a derivative. So I used a negative exponent instead of looking at a quotient. The derivative of surface area is negative 2 r to the negative 2. Make sure you subtract 1. Plus, derivative of pi r squared is 2 pi r. Notice the derivative of area is circumference. What? Just saying. And if we rewrite these in terms of algebraic formula, I'll now have negative 2 over r squared plus 2 pi r. And we see we have a singular point at a radius of 0. A radius of 0 would be a pretty lame metal drum. So, okay. Noted. Don't care. Care, but not really for the problem. So the derivative of the surface area is 0 when 0 is equal to negative 2 over r squared plus 2 pi r. I'll add 2 over r squared to both sides, and then I'm going to multiply both sides by r squared to cancel my denominator. On the left, I'll have 2. On the right, I'll have 2 pi r cubed. When I divide both sides to isolate the r, divide by 2 pi, I'll have 2 over 2 pi, which is 1 over pi equals r cubed. We'll take the cube root, and that's about 0.6828 meters. So the radius should be about 0.683 meters, and the height, if I solve for h, right, h is pi over r, 1 over pi r squared. We'll get about 0.47 meters for the height, and this is the can that will have a volume of 1 cubic meter and use the least amount of material. All right, that's it for the examples. Thanks for watching.